my name is Jordan, and today I'm going to be talking through some concepts about density functional theory that I've learned so far. So, first off, what is DFT? Well, DFT is the backbone of many first principles modelling techniques. It's an effective technique for studying large systems of atoms by directly solving approximate versions of our Schrödinger equation. And it does this by turning a many-body interaction problem down into an electron density problem. The essence of why DFT is so powerful is the fact that any observable can be calculated through the ground state electron density using functionals. But what is a functional? Well, a functional has a function as an input and it returns as a number. An example of this would be the energy of a one-dimensional simple harmonic oscillator. Here, we would need to specify a function, i.e. our wave function, in order to get a number out of our definite integral. And therefore, we can say that our energy is a functional of our wave function. Also on the board is another equation, and all I want you to take from this is the fact that the functional derivative, which is this is its definition, is different to a normal derivative. So, just a bit of history. DFT was first introduced in the mid-60s through the use of the Hohenberg and Kohn theorem. Shortly after, the Kohn-Sham equations were derived, and these are the beating heart of DFT. Through to the 90s, DFT was built upon and computing power increased, allowing for more accurate calculations and DFT calculations to be used in more and more scientific papers. So, a good starting point would be the many-body Schrödinger equation. We know that the Hamiltonian is formed of the sum of the kinetic energies and the Coulomb energies of the electrons and the nuclei. So why do we need DFT? Why can't we just solve this equation for a large system? Well, it turns out numerically we cannot do that for large systems. And this is called the exponential wall problem. I'm just going to touch upon it here. So, consider silicon in the diamond structure. The volume of its unit cell is given by approximately A cubed over 4, where A is 5.43 angstroms. A sensible way to discretize the system would be to have the points spaced out by about 0.1 angstroms. Therefore, our grid consists of 40,000 points. Now, we have two nuclei, each with 4 valent electrons. So a complete specification of our quantum state would require 40,000 to the power of 10, or 10 to the 46 complex numbers. And this is due to the fact that the many-body wave function needs to be totally antisymmetric under particle exchange, i.e. a parity operation. Obviously this is nonsensical and we can't do much matrix manipulation on 10 to the 46 complex numbers. And remember, this is for a 2-atom system. This is why we need DFT and other approximations in order to model large systems. So, we'll start with trying to simplify our equation down by getting rid of some of our constants. We do this by changing into the Hartree atomic units. Now, the Hartree energy is given at the top, and this is just the average Coulomb energy in a hydrogen atom. Now, borrowing a few concepts from semi-classical theory, we can show that the kinetic energy of an electron is on the same order of magnitude as this Hartree energy. So it's natural for us to swap to Hartree atomic units, where energy is measured in Hartrees, distance is measured in Bohrs, and mass is measured in atomic units. So as seen, if we do this, this simplifies down our many-body Schrödinger equation by getting rid of most of our constants. So now let's start talking about approximations. The first of which I'm going to talk about is the clamped nuclei approximation. And this allows us to completely ignore the kinetic energy of our nuclei. We can do this because our nuclei are much more massive compared to our electrons, and therefore won't move. What we can also do is we can shuffle around our equations and redefine our energy as the top equation. We can also redefine the Coulomb interaction between the nuclei and the electrons as just a potential from our nucleus that the electrons move through. Doing this simplifies down our Schrödinger equation into the bottom equation here. And this is called the fundamental equation of electron structure. This will become important later as we can use it for some derivations. The second approximation I want to talk about is the independent electron approximation. And this is arguably the most important. Here, electrons are now independent and we completely ignore the Coulomb interaction between electrons. This allows us to express our many-body wave function as a product of independent electron wave functions. However, we do know that our many-body wave function needs to be totally antisymmetric under particle exchange, i.e. a parity operation. Therefore, the correct way to write this is the Slater determinant shown on the board. Now, it's possible to show that from this Slater determinant we can write the electron density, which is the parameter that we really want in DFT, as the following. So, we don't know the exact form of the independent electron wave functions. However, what we do know is that the many-body wave function minimizes the energy of our system. So, let's try this for a two-particle example. Shown at the top is the two-body Schrödinger equation, and below it, the Slater determinant of these two particles. Let's now try to find the energy as a functional of our independent electron wave functions. Doing so, we end up with this quite horrible expression on the bottom. However, we can instantly cancel these two terms by identifying these two brackets. And these are in the form of our orthonormality condition, which we require. So now, we have a minimization problem with a constraint of orthonormality, leading to the use of Lagrange multipliers. Now, notice that in this minimization problem, we are using the functional derivatives, which I touched upon earlier. So, if we go through this minimization problem, and I'm skipping through quite a lot of the maths here, because we just want the true result. The bottommost equation here is just a re-expression of our orthonormality condition. And these two equations here are in the form of a Schrödinger equation. But we can simplify these down by defining some potential terms and going a bit further. So, on the left we have the Hartree potential, and on the right we have the Fock exchange potential. Now, this leads us on to these two bottom equations here. And you may notice the del squared coming in, and this is just because we have inputted that from our Hamiltonian. So, these two equations would be usable, and we would have one equation for psi1 and one equation for psi2 if we didn't have these two expressions on the right-hand side. So, to get around this, we introduce a matrix which diagonalizes our Lagrange multipliers. After doing this, we can redefine our wave functions as phi instead of psi, and we end with the two equations on the board. And these are known as Hartree-Fock equations. They're in the form of a Schrödinger equation, but with potentials instead of our many-body interaction. Now, just a note, we have now found two different potentials which describe a system. So, running the risk of killing you with potentials, I'm going to add one more, and that is the correlation potential. This owes to the fact that the probability of finding an electron near another electron decreases. This is analogous to our actual Coulomb repulsion, because obviously, if we just ignore the Coulomb repulsion overall, this would be nonsensical. So, notice here that we have exchanged the Fock exchange potential for a proxy of this potential, which only depends on one coordinate system. Also notice that for both of these potentials here, I haven't given a true analytical form of the potentials, and this is because one simply isn't known. We need to use approximations to find these two potentials. So we're getting closer to some self-consistent equations. And this is a form of the Kohn-Sham equation that we use in DFT. Now, we can start talking explicitly about DFT. I told you earlier that the Hohenberg and Kohn theorem was the introduction of DFT, and this theorem was based off three premises. The second premise is obviously true, because if we change the position of our nuclei, we expect the behavior of our electrons to change, and therefore our wave function must also change. Our third premise is also obviously true, because we all know how to calculate the energy of a quantum system. We just sandwich our Hamiltonian between our bra and ket of our many-body wave function. But what about our first? Let's try to prove this, and we'll do it via contradiction. So, let's assume that our electron density can be obtained from two different potentials, a normal version and a prime version. We're going to be using our fundamental equation of electron structure, and still remember that the electron density can be provided in this form. So let's do some maths. Finding the energy of our system, we obtain this second equation here. But what about our prime system? Well, our many-body wave function does not give the ground state energy of our prime system, and this is because our prime system has a different potential. Therefore, we can write what this energy is here is actually greater than the ground state energy of the prime system, i.e. E primed. Doing the same maths, we obtain this equation here, and we can take the two equations away from each other to get these two different equations at the bottom. Now, if these were true, we could add them together. But if we add them together, we prove that 0 is greater than 0, which is not true, and therefore we have disproved our original assumption, thus proving the first premise of the Hohenberg and Kohn theorem. Now, I just showed that the energy can be written as a functional of the electron density, but our Hamiltonian had something different. We had another potential. Adding in a Hartree potential and minimizing the energy, we find the following equation at the bottom. So you might be screaming at your screens right now, but I do know that we still did have our exchange and correlation potential. And we wrap this up in this term on the end called the exchange correlation energy. We do this because we don't know the functional form of this, and here's where all of our approximations come in. So, just to reiterate, we now have the Kohn-Sham equation, and we know that the exchange and correlation potential can be given by the functional derivative of the exchange correlation energy. So, the approximation for this we use is called the local density approximation, where we assume that the material behaves like a homogeneous electron gas, which is similar to a free electron gas. However, the electrons move in a constant background potential. Now, I'm not going to be deriving these results. However, we do have these two expressions on the board. The bottommost is the correlation energy, and the keen-eyed might see that it looks a bit funky in comparison to the exchange energy. And this is because we numerically derive this. In this equation, Rs stands for the Wigner-Seitz radius, and is the radius of a sphere occupied on average per electron. But how do we use this for real materials? Homogeneous electron gases have a step-like electron density. Obviously, a real normal material won't act like a homogeneous electron gas. So, let's assume our material had a smoothly varying electron density given by the bold line. What we could do is we could split this system up into many different regions and approximate each region as a homogeneous electron gas. Doing this allows us to write a small part of the exchange and correlation energy as the following fraction. Which is good because we know a form of the exchange and correlation energy for the homogeneous electron gas. So we can find this by just integrating the previous expression. So now we have the exchange and correlation energy. So we can just do a functional derivative and get the exchange correlation potential. And without realizing it, we've derived a self-consistent set of equations that we can use in DFT. The first of which up here is called the Kohn-Sham equation. We now have all of our different potentials and a way of finding the electron density. So, let's put this all together in a DFT flowchart. We need to start this by having a nuclear potential. And we get this by specifying nuclear coordinates given by the big bold R. These are usually obtained through crystallography data. However, what one can do is we can vary the sites of the nuclear positions and find the energy of the system. Plotting the energies of the system, we can find which is the minimum, and this will be the structure of our material. So, it's then standard to have an initial guess of the electron density, which is usually done by adding up all of the individual isolated atoms' electron densities. And then we go through our iterative process. We find our potentials, we solve our Kohn-Sham equation for our wave functions, we then use these wave functions to find a new electron density, and we try to find a convergence between our new and our old. Notice that this is an iterative process while we try and find convergence. when we find convergence, we now know the electron density of the system, which through different functionals allows us to find the other observables of the system. So let's look at some real code. This was provided by Julie Staunton as an example for me. So, as seen up here, we have the basis, i.e. what atoms we have in our system. So this would be just for vanadium. And vanadium is a BCC lattice, so the N group just gives us the specifier for what structure it is. And from here, we can define what the coordinates of each of our vanadium atoms are. So, then we have a structure file in which we can specify which electrons act as core electrons and which act as more valent electrons, allowing us to get a more accurate representation of how the electron density is spread in the system. So, going through our iterative process, we have a number of iterations on the left, and then we see that it slowly comes to a very good convergence. The code then spits out many different parameters that we can use to model our system. So, credit where credit's due. Most of this talk was based off the book Materials Modeling Using Density Functional Theory, and I'd recommend anybody pick up this book if they're interested in the topic. I'd also like to thank Dr. Julie Staunton for providing some of the example data.